All right. So the paper we are group 8, and the paper we're presenting about today is called DreamBooth, Fine-Tuning Text-to-Image Diffusion Models for Subject-Driven Generation. This is a Google research paper with the lead author also coming from Boston University. So I'm going to walk you through an agenda of what we're going to present today. We'll start with an introduction to few-shot image generation and then discuss the research gap that this paper fills. I'll cover some high-level methodology before we get into the solution specifics to hopefully clarify any doubts you might have. This paper has a lot of results and examples, so we'll make sure to walk through each one of those and then discuss some ablations that prove the effectiveness of their technique before we talk about some limitations of the paper. And then at the end, we'll walk you through some of our own experimentation that we did with this code. So just to start, this is a paper or a figure from a GAN paper, but the same idea applies to diffusion models. So few-shot image generation, we could imagine you start with a pre-trained generator, let's say Imagen. In this case, we're just asking it to generate these photorealistic faces. However, we want it to learn a certain art style. In this case, it's this sort of painting art style, and we want it to be able to reproduce these faces, but in this style. This is not representative of a full data set. This is only 10 images. We're giving it few images to learn from. And the goal is to learn a new model that is able to produce these original source images, but with adapting the style from this few-shot target domain. So this is just the general idea. And what we find is that if you give this task to most text image diffusion models, it actually fails. They're unable to perform this few-shot learning. So with them, there's no efficient method to sort of inject subjects into the model training. This is because of two major problems, being overfitting, where the model just starts to reproduce the original input images, or language drift, where the language semantics get messed up within the model and you start getting things you don't ask for, and it causes some undesired side effects. The best example of a paper injecting subjects into the training was actually a GAN, which was able to reproduce the same face given around 100 images, which this is limited to just the face, and it's 100 images, so it's not quite few-shot. So the authors saw that this was a problem that existed, and they sought a way to solve it. So their major contribution was they created a new efficient few-shot fine-tuning technique that preserves semantic class knowledge. Notably, it's a fine-tuning technique. It is not an architectural difference. They just use Imagen and they fine-tune it in a specific way with their own customized loss function. Here, semantic class knowledge is prior knowledge that the model already has. Let's say in the dog category, when you try to fine-tune it to learn a dog, it doesn't need to relearn everything a dog does. It already has that knowledge. And because it maintains this semantic class knowledge, the tuning actually only requires 3 to 5 examples, making it actually few-shot. They also created this new niche problem to explore diffusion model capabilities that they call subject-driven generation. It's not quite a quantitative model to compare between different architectures. It's a niche little problem that allows them to demonstrate certain capabilities of diffusion models that you don't see anywhere else. And the goal of this is to maintain object fidelity in new context. I'll demonstrate this on the next slide. So given these input images to tune on, only 3 of the same clock with a couple different backgrounds, along with prompt retro style yellow alarm clock with a white clock face and a yellow number 3 on the right part of the clock face in the jungle. We're asking it to reproduce this clock here in the jungle. If we give this to DALL-E, we see that it overfits on the training data. It just starts giving the same white background, and it only captures the high-level details of the clock. So it still knows it's a yellow alarm clock, but it's not quite the same one. So it fails on applying a new context and maintaining object fidelity. Imagen was slightly more robust. We see that it actually takes in the jungle context and places the clock in the jungle, but like DALL-E, it just captures the high-level details of the clock and does not maintain object fidelity. However, when you fine-tune using this DreamBooth technique, we see that it faithfully reproduces the input clock. We see the same big yellow 3, and it places it into new unique contexts. So here's a more robust figure demonstrating the capabilities. If we take these 4 input images of a dog at a photo shoot, instead of simply photoshopping a background behind them, you can ask the model to place your dog in the Acropolis or swimming, sleeping. And what I like about these is we see that their swimming and sleeping poses are not remotely seen in these input images. They're completely unique, but because the model takes advantage of the semantic class understanding of dog, it knows what a dog swimming and sleeping looks like. So it's able to apply that here. And now in this example, we just take a couple pairs of sunglasses and we realistically place them into new contexts. And the best example here is on top of snow, where we can see that it's not just copied and pasted on top of snow. We see it's actually sitting into the snow as if it were actually there. So we see that in these examples, they've maintained the object fidelity and applied them to new contexts. So this is a really cool capability, but I'm going to pass it off to Niall, and he's going to explain to you guys how they actually accomplish this.
Right. So as Joe mentioned, the main idea of this paper is essentially trying to improve few-shot text-guided diffusion. And they do this not by introducing a novel architecture, but by fine-tuning an existing pre-trained diffusion model, namely Imagen. So the high-level idea is you have some input. You have about 3 to 5 images of a novel class the model has never seen before, and you have an off-the-shelf diffusion model. So DreamBooth is really more of a fine-tuning technique, where after you do this fine-tuning, the output that you get is a diffusion model that's able to generate images of this novel class, but there's also a unique identifier. And this is essentially a text or a list of strings that we use to bind, that's bound to the new subject. So we use this unique identifier to reference the subject when prompting the diffusion model to generate a new image. So we'll start with looking at some of how they solve some of the identified gaps. So as Joe mentioned, one of the big ones is that there's no efficient method to inject subjects into the model training or the model knowledge. So the first contribution the authors make to tackle this problem is the rare token identifier. So the real question is, how do we refer to this new subject when trying to generate a new image? Well, with the image space, it's pretty straightforward. If we want to train a diffusion model to learn to generate images of a new subject, we can simply pass it images of the new subject. The problem more comes with the text space of how do we prompt the model in the text space to generate images of this new subject without generating any other irrelevant objects. So we note that we're using Imagen, we're using a pre-trained diffusion model. So there's already vocabulary. This model has already been trained on the English language. It understands semantic understanding of text prompts for image generation. So the goal really is to teach this model how to generate images of a new subject and also implant this subject in the text vocabulary. So we have a way of referencing it, prompting it through text, and being able to generate new images of this subject. The way that the authors structure this is by using this syntax right here. They say a, and then a class, or we call a unique identifier, and the course class noun. So we can look at this figure for reference. If this is our novel subject of images that we want to generate, we prompt the model by saying a v dog on the beach. V here is the unique identifier, and this goes through our diffusion model. It takes in text, and it's able to output the image of this novel class on the beach. And we see this similarly with walking on a colorful carpet as well. So what is this unique identifier, and how do we obtain it? So let's look at some naive approaches.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
Just to build some intuition. Firstly, we could think of just using some English word to describe this new class. So we could use the word unique or special anytime we want to generate images of this novel subject. So we could say a unique dog or a special dog. The problem with that is that almost every diffusion model is pre-trained on the English lexicon. So almost every single English word has a strong prior meaning. The model already has some understanding of what unique looks like and what special looks like. So it may not fully understand that we're using this word to refer to the subject that it has been fine-tuned on. So what if we go on the complete opposite direction? What if we use a unique identifier that has basically no prior information in a pre-trained diffusion model? So in this case, there's probably very few, if any, text prompts containing this string in a pre-trained model. So we could maybe use this as a unique identifier because there's no prior information about this string. The problem with that is that these nonsense identifiers lead to literal artifacts in image generation. So the authors found that the letter X or the letter Y, maybe even the number 5, would be inside the generated images when we're using these nonsense identifiers. So we have a problem of too much prior information in this example and too little prior information in this example as well. So the solution the authors note is that we will perform a rare token lookup in the vocabulary for the diffusion model. So we essentially look at every single possible token that the model is able to understand and find the tokens that occur the least during training, or essentially have the weakest prior in the text space of a diffusion model. Now this is just in a token, right? It's a string of text that's been embedded into a token space. So if we invert this rare token, what we get is plain text. And usually the authors found that limiting this plain text unique identifier to about 1 to 3 characters yielded the best results. And it's that simple. All we need to do is use this plain text as a unique identifier, and that's how we solve the problem of injecting the fine-tuned subject into the model. So again, using this figure for reference, in this case, the V, or the unique identifier, would be this 1 to 3 character plain text. We'll see later on in the presentation that SKS is very commonly used. It seems to be a token that's very rarely used during training, so it would be very common to see during inference that the prompt would say a SKS dog on the beach, and SKS would denote to the model that we want to generate this new subject, not just any old dog. So great, we kind of have a way now of injecting a novel subject that a diffusion model hasn't seen before into both the image and the text space. But unfortunately, that isn't enough for few-shot image generation. There's the problems of overfitting and language drift. So they introduced this loss to solve those problems, but before I get into this mouthful, let's look at what overfitting and language drift actually look like in image generation. So we have one example here of what overfitting looks like. You have a pre-trained diffusion model, and you fine-tune it on these 3 images of this dog. Now, without using this loss, we can see that these images are overfit to the input image. The dog is always laying down with his paws in front of him, and he's laying on some sort of object. It's a frontal view, so there's not a lot of variation. Whereas when we use this loss, we can see that the model is capable of generating images of the dog sitting, it's standing, it's at different backgrounds, it's at different viewing angles, which is what we expect. The second hurdle is language drift. And this kind of comes from natural language processing, where when you fine-tune a model, it loses the prior information it had already learned. So in the case of image generation, we can see if you take any vanilla model, let's again think of Imagen because this is the model they're using here, and we prompt Imagen to generate a dog. We know that any old diffusion model is very adept at generating different breeds of dogs, different viewpoints, backgrounds, etc. However, if we fine-tune a model on just these 3 images of a dog, and we again prompt it to generate a dog, the problem is that it loses all prior information about how to generate images of a dog. Now we only have images of the fine-tuned subject. So again, this loss, when we implement it, we can see that it preserves the prior information of being able to be fine-tuned on a subject while still generating novel and distinct images of dogs. So they achieve this by using an autogenous class-specific prior preservation loss. So like I said, it's kind of a mouthful. So let's break down what each of these words essentially means. So autogenous means coming from oneself or generated from oneself. So we'll be using our own generated images inside this loss. Now, the second thing is that I've been noting a lot, we're using a pre-existing or a pre-trained diffusion model. So this pre-trained diffusion model already has prior information about specific classes. It knows what a dog looks like. It knows what a cat looks like. And we want to preserve this information. So we want to preserve the prior class-specific information, and we do this using some self-generated images. So let's walk through the entire process of what this looks like during a training loop. So to start, what we have is we have the model that we want to fine-tune, right? This is an Imagen model that we're fine-tuning. It takes in some text, and it generates a 64 by 64 resolution image. So what we do is we take some of our input images, about 3 to 5 images of a novel subject, and we take a noise map. We prompt it with a V dog, so this is the rare token again. And what we expect is that our model should be able to take this noise map and generate very similar images to the input. Now, this is essentially, actually exactly standard diffusion loss. This is something we've all come to know and love, and we should be quite familiar with. So we have X here, which is our input images, and we have C here, which is a conditioning vector. In this case, it's text. So based on this text, what we have is we take our input image and we add some sort of noise to it. Now we want to train some sort of diffusion model to take in a noised image and text as input, and it should be able to generate an image that's very similar to our input images. So essentially we take our predicted image, we take our input image, and we do a pixel-wise reconstruction loss to supervise this generation process. Again, this is just standard diffusion loss. This should be quite familiar. Now, here's the second part that the paper novelly introduces. What we should do at the same time is we should take our frozen ImageN model, and this is locked, so the weights are frozen, it's completely off the shelf, this model is not being fine-tuned, and what we do is we take a simple noise map and we ask ImageN to generate an image of a dog. And we know that ImageN is quite a high-level diffusion model. It should be able to generate high-fidelity, high-quality images of dogs. So we can use this almost as like a pseudo-label. We can use this as our ground truth input images. What we do now is we take another noise map, and this time we prompt our fine-tuned model. So this is the model we are trying to fine-tune, and we ask it to generate a dog as well. So what we would expect is that because this is an ImageN model, we're fine-tuning it, it's already pre-trained, it should still be able to generate high-fidelity, high-resolution images of dogs. And the way that we supervise this is exactly the same as standard diffusion loss. You'll notice that this term in green and this term in red are exactly the same. There are some small differences. In this case, we take CPR, which is our text prompt in this case, which is just a dog without the unique identifier. And we have some prior images, which is XPR, which goes here. So all we're essentially saying is that this fine-tuned model should be able to take a noised image of just a dog, and it should be able to generate very similar images to what the original ImageN model was able to generate. And again, we use pixel-wise reconstruction loss to supervise this. So essentially, there's two things happening at the same time here. In the green box, what's happening is the fine-tuning of the model. We have some novel images. We want our fine-tuned model to be able to generate these images. The red box is more of the prior preservation aspect, where we know our model can generate images of dogs, and we want to preserve that capability, and we use that using this loss. So lastly, there's a little bit of a lambda term here. You can set the weight to maybe give more weight to this loss or not. The authors set it to 1, so it's an equal weight. But on top of this, there's essentially just this loss and the rare token identifier. And those are the only two things the author used to really improve few-shot image generation using diffusion models. So they achieved some astounding results, and I'll pass it to Mitchell to go over what these results look like.
Thank you, Niall. Can everybody see my screen? I think so. All right, so there are lots of possibilities to the semantic modification of a subject instance. Some of these include recontextualization, like drawing the model in a different place, color modification, drawing the subject from a different angle, lots and lots of possibilities. The idea behind this paper was that given a pre-trained model and utilizing the training process that Niall just talked about, you can take in a sentence structure with your V. Niall mentioned SKS is one of the possibilities, but we'll just use V in these examples. And then you can output a unique image preserving the subject instance features. And then you can even do like cross-domain features across classes. And we'll show some instances of that. So recontextualization. Given the trained model, we can pass in a sentence to it containing the subject class. And in this instance, it's backpack. And you can also pass in its unique identifier V with a different sentence structure. For best results in recontextualization, the typical sentence structure is kind of like so. You want to have A and then V, and then you want to have your class. In this case, it's backpack. And then you want to give it like the specific domain that you want to capture it in. And so here we kind of show that you can put it in specific places. You can have a different subject instance, and you can put it in generalized places like the ocean. And then you can even have it recontextualized to performing an action like pouring tea.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
So artistic renditions. When passed the sentence structure of a rare token plus your class, and then you can say in the style of a specific artist, it can draw the subject instance in a different domain, but notably with a unique image. So this can go on for many different other kinds of artists. And then you can even kind of have a cross domain of what you're doing. It's not, doesn't have to be just artistic. You can even say like a sculpture of, and it'll produce that, but it'll be unique. So expression manipulation. The model is also able to learn the emotional state features, extract them, and implant them on the subject instances. We can clearly see that it doesn't really look like he's having a good time, having a bad time, or anything. He's just kind of chilling out there. So given the sentence state with your rare token identifier and then your class, you can kind of redraw it to show any kind of emotional state that the model has learned. You can see in the depressed image, he looks kind of depressed. In the barking image, he's barking, screaming, things like that. And you can see that even though the input image doesn't have an open mouth, it knows what the open mouth of a dog looks like, so it's able to implant them onto there. View synthesis. The subject instance is also able to be viewed from novel viewpoints. That means the input images don't have input of that viewpoint. So what this means is that the model was able to learn the class features of a cat from all angles and be able to implant them onto the cat from any direction. So to do this, you would have your rare token identifier plus your class, the cat in this instance, and you can say seen from the direction, top, bottom, side, behind, things like that. Accessorization. So this is certainly like an interesting capability of the model. It comes from the prior. You can bind words to feature classes and pairs. Given the sentence structure, a token, for a token identifier plus your class, dog in this instance, you can say wearing an accessory. And that accessory can be a chef outfit, purple wizard, or angel wings. And the important thing to note here is that, like the glasses in the snow, we can also see that the shadows are drawn in such a way that the outfit is taken into consideration. With the wizard outfit, the shadow is lengthened. With the angel wings, the shadow has kind of a space between them where you can see that there's no more shadow. So property modification. In the simple case with the car, the descriptor is applied before the token, and that class will modify the appearance of the subject instance. So you can just see a color, token, car, and then that color will be appeared. And you can also see that the output is also unique. It's not the exact output domain that it was input. It's going to be unique every time. And so something more complex like a dog, and saying a cross of a token, dog, and a target species, your cross domain, you can see that the dog's facial features are preserved on the output of the hippo. So we'll pass it out over to Shane.
Okay, to go over some ablations, we have an example of these sunglasses, and we want to see how the class noun prior is affected. So the first test they did is they just completely removed the class. So they just have A followed by the rare token. And you can see that it wasn't able to generate the sunglasses at all. Next, we have an incorrect class noun. So A rare token followed by dog. And it was able to generate the sunglasses for some of them, but it still also remained had some prior knowledge of a dog. And so it kind of got them mixed up. And then finally, for the working version, they have a rare token followed by the class, and you can see they were all working correctly. So now to go over some main failure points of this method. So we have these images of pink backpacks in a forest. So the first failure point they found was incorrect context synthesis. So they gave it prompts like the backpack in the ISS or the backpack on the moon, and it wasn't able to generate these contexts. And the idea behind that is the priors for these contexts weren't strong enough, or the combination of the subject and the context was too rare for the model to be able to generate it. Now we also have the color changing in our backpacks from the context. So we can see here with this one very clearly, the pink changed into brown. And this is because the prior for the context itself was too strong and it started modifying the subject. And then lastly, we have overfitting. So we gave it original images of it being in the forest, and we prompted it with the same prompt, the backpack in the forest, and it wasn't able to generate any new novel images. These look very similar to the original inputs. So now to go over some limitations for it. So the model will learn certain subjects better than others. So say, for example, you wanted to train a picture on your own cat. It would learn that subject a lot better than more rare and complex subjects. Another issue was image noise with the hallucinated features. We'll see that more in the experimentation because we had some of those issues. That can come from a variety of reasons, coming from the prior not being strong enough or the prior being too strong, issues in the super resolution parts of the model where it scales up the images. And so that can have a lot of reasons. Some limitations with the paper itself is that they didn't provide any suggestions on preventing malicious use. Obviously, this is kind of a big problem, and you can do a lot of stuff with these models, and there's no inherent filters that they gave. Another limitation with the paper was there was no quantitative results, so we can't compare it with other models to see how well it actually did with caption accuracy and photorealism. So now to go on our own experimentation. So we found an implementation of DreamBooth using Hugging Faces diffusers GitHub. A couple main differences. They used Stable Diffusion v1.5 as their model instead of Imagen. And also the rare token, it wouldn't automatically choose it. You would have to provide it yourself. So they would recommend SKS for the rare token. And then for the hyperparameters, we mainly followed all the recommendations in the instructions for the GitHub for setting them up. So the first test we wanted to do is we just wanted to make sure that we can replicate similar results from the paper. So we used Joe's dog. And here were the input images we gave it. Notably, the images were mainly focused on the subject itself. It didn't have too much background and other stuff inside it. So the first step when you're training these is you need to make the regularization images. That's going back to what Niall explained with the prior preservation loss. You need generic photos of your class, which in this case was dog. And we had 96 total images of that. And then now for the actual training itself, when we ran the training, we got pretty okay results with this one. We can see some of these issues with hallucinated features. The images weren't very photorealistic, but it generally looks pretty similar to Joe's dog. And then we also have a bit better example where you can see it's a bit more realistic. It looks a bit more closer to his dog. Now, to give it a bit more of a difficult test, we decided to use Nitro, which is our mascot. And so these were the input images. We had issues with the input images having too much people in the background, so we had to crop the images as closely to him as we could. And then we also found some interesting things with the regularization images. So we would have the classic pictures of what we would think of a knight, but then we would also have random portraits of people and also horses involved in it. So we increased our regularization images to hopefully try to not let the model focus more on these other images that aren't really similar to our images. And so when we trained it, here are the results. So we used a photo of a night at the beach, and it was pretty okay. You can see the lettering got a bit messed up, but the overall shape and figure was pretty close to our input images. And same thing with this one. It's not nearly as good, but you can see the coloring and the overall shape. But we can also see some issues with the prior of just riding a bicycle being shown. So if you think about it, the context of a knight riding a bicycle probably wasn't, probably didn't have many occurrences in the data set, like in the normal data set. So we can see normal people's like jeans and shoes and whatnot showing up in here. And so, yeah, that was our presentation. Any questions?